Tutorial number 3, Defining Lambda++, Lesson 1. Here we add call with current continuation, call CC, to the definition of lambda completed in Tutorial 1 and call the resulting language lambda++. While doing so, we will learn how to define language constructs that abruptly change the execution control flow. Take over the lambda.k definition from Lesson 8 in Tutorial 1, which is the complete definition of the lambda language, but without the comments. Call CC is a good example for studying the capabilities of a framework to support abrupt changes of control, because it is one of the most control-intensive language constructs known. Scheme is probably the first programming language that incorporated the call CC construct, although similar constructs have been included in many other languages recently in one form or another. Here is a quick description of call CC. Call CC applied to expression E passes the remaining computation context, packaged as a function, say k, to E, which is expected to be a function. If E passes anything to k, then the current execution context is discarded and replaced by the one encoded by k. If E evaluates normally to V and passes nothing to k, then V is returned as a result of call CC of E and the execution continues normally. For example, we want the program call CC jump.lambda, namely to evaluate to 15, not 17. Indeed, the computation context, whole plus 10, is passed to call CC's argument, which then sends it a 5, so the computation resumes to 5 plus 10. On the other hand, the program call CC not jump.lambda evaluates to 17. If you like playing games, you can metaphorically think of call CC of E as saving your game in a file and passing it to your friend E. Then E can decide at some moment to drop everything she was doing, load your game and continue to play it from where you are. The behavior of many popular control changing constructs can be obtained using call CC. The program return.lambda shows, for example, how to obtain the behavior of a return statement which leaves the current execution context inside the function and returns a value to the caller's context. This should evaluate to 1 in spite of the recursive call to f and of the division by 0. Note the return is nothing but a variable name, but one which is bound to the current continuation at the beginning of the function execution. As soon as 1 is passed to return, the computation jumps back in time to where call CC was defined. Change -3 to 3 and the program will loop forever. Call CC is quite a powerful and beautiful language construct, although one which is admittedly hard to give semantics to in some frameworks. But not in K. Here is the entire K syntax and semantics of call CC. Let us first discuss the annotated syntax. We declare call CC strict because its argument may not necessarily be a function yet, so it may need to be evaluated. As explained above, we need to encode the remaining computation somehow to pass it to call CC's argument. More specifically, since lambda is called by value, we have to encode the remaining computation as a value. We do not want to simply substore computations to val, because there are computations which we do not want to be values. A simple solution to achieve our goal here is to introduce a new value construct, say CC, from current continuation, which holds any computation. Note that, inspired from SDF, K allows you to define the syntax of helping semantic operations like CC more compactly. Typically, we do not need a fancy syntax for such operations. All we need is a name, followed by open parentheses, followed by a comma-separated list of arguments, followed by close parentheses. If this is the syntax that you want for a particular construct, then K allows you to drop all the code surrounding the terminals. The semantic rules do exactly what the English semantics of call CC says. Note that here, unlike in our definition of lambda in Tutorial 1, we had to mention the cell k in our rules. This is because we need to make sure that we measure the entire remaining computation, not only a fragment of it. For example, if we remove the k cell from the two rules above, then we get a call CC which is allowed to non-deterministically pick a prefix of the remaining computation and pass it to its argument, and then, when invoked within its argument, a non-deterministic prefix of the new computation is discarded and replaced by the saved one. Wow, that would be quite a language. Would you like to write programs in it? Consequently, in K we can abruptly change the execution control flow of a program by simply changing the contents of the K cell. This is one of the advantages of having an explicit representation of the execution context, like in K or in reduction semantics with evaluation context. Constructs like CC are very hard and non-elegant to define in frameworks such as SOS, because those implicitly represent the execution context as proof context, and the latter cannot be easily changed. Now that we know how to handle cells and configurations and use them in rules, in the next lesson we take a fresh look at Lambda and define it using an environment-based style, which avoids the complexity of substitution and is closer in spirit to how functional languages are implemented.